far beyond Neptune, in the frozen outer reaches of our solar system, there is a world that looks like nothing you have ever seen before. It is not round. It is stretched, pulled, elongated into a shape so distorted that if you could hold it in your hands, it would resemble an oversized football. The reason it looks this way is simple. It is spinning. Fast. So fast that it completes one full rotation in roughly 3.9 hours. That is faster than any other large world in the solar system has any right to spin. Gravity wants to crush it into a sphere. Rotation is winning. And the story of how this world ended up this way reaches deep into the violent past of the outer solar system. If you're the kind of person who enjoys exploring the strangest worlds in our universe, then consider tapping the like and subscribe button. We genuinely appreciate every one of you that supports this channel. Now, are you comfortable? Let's begin. There is a rule that governs every large object in the solar system. If a body is massive enough, gravity will shape it. Not quickly, not dramatically. But over millions and billions of years, the relentless inward pull of its own mass will compress it, smooth it, round it off, until it settles into something close to a sphere. Rock flows, ice deforms, metal yields. Given enough time and enough mass, gravity always wins. This is not a theory waiting for proof. You can see it everywhere you look. Earth is a sphere. Mars is a sphere. Jupiter, Saturn, the moons of the outer giants, all of them are rounded by their own gravity into shapes that are either perfect spheres or close enough that you would never notice the difference with your eyes. Even on the smaller end of the scale, once a body crosses a certain size threshold, gravity takes over. The irregular lumps and jagged edges you see on small asteroids and comets smooth out. Peaks collapse, valleys fill in. The body settles into a shape dictated by the balance of forces acting on it from within. The technical term for this state is hydrostatic equilibrium. It is the condition a body reaches when its gravity, its internal pressure, and its rotation have negotiated a stable arrangement. And for most objects, the result of that negotiation is something very close to a sphere. This principle is so fundamental that it became part of the official definition of what a dwarf planet is. When the International Astronomical Union created the dwarf planet category in 2006, one of the explicit requirements was that the object must have sufficient mass for its self-gravity to have overcome rigid body forces and achieved hydrostatic equilibrium. In simpler language, it must look roughly round, not perfectly round, not polished smooth, but round enough that an observer could tell gravity has done its work and shaped the body into something balanced and settled. Look at the dwarf planets we know, and the rule holds without exception. Pluto is round. It has a diameter of roughly 2,377 kilometers. Its surface is a patchwork of nitrogen ice, methane frost, and frozen carbon monoxide. And beneath the exotic icy shell lies a rocky core that may still harbour a subsurface ocean of liquid water. Pluto orbits at an average distance of roughly 39 astronomical units from the Sun, in the cold, slow darkness of the outer solar system. It is ancient, it is far, and it is round. Gravity shaped it billions of years ago, and it has stayed that way ever since. Eris is round, roughly the same size as Pluto, perhaps slightly smaller depending on the measurement. Eris orbits even further out, in the scattered disk beyond the Kuiper belt. Its surface is covered in methane ice, so reflective that Eris is one of the brightest known objects in the trans-Neptunian region. And despite its extreme distance, sometimes more than 90 astronomical units from the Sun, every observation confirms the same basic fact. Eris is round. Gravity shaped it. Haumea is round. Sitting in the Kuiper belt at an average distance of roughly 45.5 astronomical units from the Sun, Haumea has a surface of frozen methane and possibly ethane. It is slightly smaller than Pluto, dimmer, less studied, and harder to observe. But its shape has been constrained by stellar occultation measurements and thermal models, and those constraints all point to the same conclusion. Haumea is round. Gravity shaped it. Ceres, the only dwarf planet in the inner solar system, is round. Orbiting in the asteroid belt between Mars and Jupiter, Ceres has a diameter of roughly 940 kilometers. It is composed largely of rock and water ice, and its surface is dotted with bright salt deposits that hint at a subsurface brine layer. Ceres is much smaller than Pluto and much closer to the Sun, but it is still large enough for gravity to have won. It is round. The pattern is consistent, and the pattern is universal. Every dwarf planet that has been measured, imaged, or studied in detail obeys the same rule. If you are large enough to qualify as a dwarf planet, if your gravity has pulled you into hydrostatic equilibrium, then you are round. Gravity demands it. Physics enforces it. Every known example confirms it. And then there is Haumea. Haumea does not obey the rule. Not even close. It is not round. It is not slightly out of round. It is stretched along one axis so dramatically that its longest dimension is more than twice its shortest. If you could see it from a spacecraft, drifting in the blackness of the outer solar system, it would not look like a planet. It would not look like a moon. It would look like something between a rugby ball and an oversized potato, tumbling through space with a shape that no planet in any textbook has ever displayed. That shape alone would be enough to make Haumea one of the strangest objects in the solar system. But the reason it looks this way is what elevates it from strange to extraordinary. Haumea is spinning faster than any other known dwarf planet. Spinning so fast that the outward push of its own rotation has physically pulled its body out of the spherical shape that gravity would normally impose. It completes one full rotation approximately every 3.9155 hours. Not days, hours, roughly 4 hours for one complete turn. For a body more than 1,000 kilometers across, composed of rock and ice, sitting in the frozen outer solar system more than 40 astronomical units from the Sun. That is an almost incomprehensible rotation rate. To understand how extreme this is, you need to see it next to the other dwarf planets. Pluto rotates once every 6.4 Earth days. It turns so slowly that one Pluto day lasts more than a week by Earth standards. Eris takes roughly 25.9 hours to complete one rotation, just slightly longer than an Earth day. Haumea spins once every 22.8 hours. Ceres completes a rotation in roughly 9 hours, the fastest of the group aside from Haumea. Now consider Haumea, 3.9 hours. It rotates more than 39 times faster than Pluto. It spins nearly 6 times faster than Haumea. It turns so rapidly that if you were standing on its equator, which is of course impossible for many reasons, the surface beneath your feet would be moving at a velocity where the centrifugal force pushing you outward would be a significant fraction of the gravitational force pulling you down. You would weigh less on Haumea's equator, not just because the body is small, but because the rotation is actively working against gravity. The effect becomes even more extreme at the tips of Haumea's longest axis. On a spherical body, every point along the equator sits at the same distance from the rotation axis and experiences the same centrifugal push. On Haumea, the equator is not a circle, it is an ellipse, stretched along one direction far more than the other. The points at the far ends of the longest axis are further from the center of mass than any other points on the surface. They are moving faster through space as the body rotates, and they experience the greatest outward push of any location on the body, while simultaneously feeling a slightly weaker gravitational pull because they are farther from where most of the mass is concentrated. This creates a gradient of effective gravity across Haumea's surface that has no parallel among the other dwarf planets. At the poles, gravity operates almost unopposed by rotation. At the equatorial tips of the longest axis, gravity is at its weakest, and centrifugal force is at its strongest. The difference between those two locations is not a minor correction. It is a fundamental feature of the body's physics, a gradient steep enough that if you could somehow walk from Haumea's pole toward the tip of its longest axis, you would feel yourself growing measurably lighter with every step. Not because you were climbing uphill, but because the ground beneath you is being pulled outward by the spin, while gravity weakens with the increasing distance from the center of mass. This gradient matters because it defines where the body is most vulnerable. If Haumea were spinning even slightly faster, the tips of the longest axis are where material would first begin to leave the surface. They are the weak points in Haumea's structure, the locations where the balance between gravity and rotation is thinnest. They are, in a very physical sense, the places where Haumea is closest to losing hold of its own body. None of the other dwarf planets spin fast enough for this to matter. Their rotations produce mild flattening at the equator at most, the kind of subtle equatorial bulge that Earth has, roughly 21 kilometers wider at the equator than from pole to pole, so small that the planet still looks perfectly round from space. On Haumea, the effect is not subtle. It is the dominant feature of the entire body. The rotation is not a minor correction to the shape. It is what defines the shape. To understand where Haumea sits and why this matters, we need to look at its neighborhood. The Kuiper Belt is one of the least familiar and most scientifically important regions of the solar system. It begins near the orbit of Neptune at roughly 30 astronomical units from the Sun, and extends outward to approximately 50 astronomical units or more, depending on where you draw the boundary. It is not a thin, flat ring like Saturn's famous bands. It is a vast three-dimensional region, shaped roughly like a flattened donut, populated by icy bodies ranging in size from grains of dust to worlds more than 2,000 kilometers across. The objects in the Kuiper Belt are old. They are among the most ancient, least altered materials in the solar system. When the solar nebula, the vast cloud of gas and dust that gave birth to the Sun and its planets, collapsed and flattened into a disk more than 4.5 billion years ago. The inner regions of that disk swept their material into the rocky and gas giant planets. The outer regions were different. They were colder, slower, less disturbed. Much of their material was never swept up into a large planet. Instead, it remained in orbit, frozen at temperatures hovering around minus 230 degrees Celsius, preserved in a state that is closer to the original conditions of the early solar system than anything else we can study. The Kuiper Belt is a fossil bed. Its objects are fragments of the disk that built the planets, frozen in place at the edge of the Sun's influence. Neptune's gravitational influence carved the inner boundary of this region and scattered some objects into more extreme orbits, creating the scattered disk that extends even further into the darkness. But the classical Kuiper belt, the dense core of the population, sits roughly between 30 and 50 astronomical units. It is home to Pluto, to Marke, to Haumea, and to thousands of smaller bodies that remain uncharacterized. This is the neighborhood Haumea occupies, and its orbit through it is not simple. Haumea follows an elliptical path that carries it from a closest approach of approximately 34.4 astronomical units from the Sun to a maximum distance of roughly 51.5 astronomical units. Its average distance is about 43 astronomical units. The orbit is tilted steeply relative to the plane of the solar system, inclined at roughly 28.2 degrees, one of the higher inclinations among the known dwarf planets. A single orbit takes approximately 285 Earth years. Haumea has not completed a single trip around the Sun since it was first recorded in data. At its current pace, the last time it was at this position in its orbit, Mozart had not yet been born. And throughout that immense, slow journey around the Sun, it spins, once every 3.9 hours, over and over, without interruption, without slowing, in the frozen dark, at temperatures of approximately minus 241 degrees Celsius, roughly minus 402 degrees Fahrenheit. This elongated world turns and turns and turns, presenting a completely different profile to any distant observer every 2 hours as its long axis swings toward and then away from the line of sight. The discovery of Haumea itself came wrapped in controversy. In late 2004, a team at the Palomar Observatory, led by Caltech astronomer Mike Brown, identified a bright, fast-moving object in survey data taken with the Samuel Oschin telescope. It appeared in earlier images, but had not been flagged as significant. Brown's team recognized that this was something large, distant, and unusual. A Kuiper belt object with photometric behavior, unlike most others. They nicknamed it Santa because the analysis was happening near the holiday season, and they began preparing a formal announcement and follow-up observations. Before they could publish, a second team intervened. In July 2005, Jose Luis Ortiz and colleagues at the Sierra Nevada Observatory in Spain announced that they had independently found the same object in their own archival data from 2003. The timing was explosive. Ortiz's announcement came just days after Brown's group had submitted a conference abstract that hinted at the discovery without giving precise coordinates. What followed was one of the most contentious priority disputes in modern planetary astronomy. Brown's team accused the Ortiz team of having accessed their telescope observation logs before making their announcement. The Ortiz team denied it. Investigations were launched. The International Astronomical Union ultimately listed the discovery date as March 7, 2003, and credited the discovery location as the Sierra Nevada Observatory in Spain, but notably declined to name an official discoverer. The naming rights reflected a compromise. The name Haumea, after the Hawaiian goddess of fertility and childbirth, was proposed by Brown's team and accepted by the International Astronomical Union in September 2008. Brown's team had already discovered 2 moons in 2005 and named them at the same time. The controversy matters for the historical record, but what matters more for our purposes is what both teams found when they studied this object closely. Because from the very first measurements, Haumea announced itself as something wrong. The object was bright, remarkably bright. Most Kuiper Belt objects have dark surfaces, coated in a mixture of ancient organic compounds and irradiated ices that absorb most of the faint sunlight reaching them. Their albedos, the fraction of light they reflect, are typically low. Haumea was different. It reflected far more light than expected for an object at its distance. Spectroscopic observations confirmed the reason. Haumea's surface is dominated by nearly pure crystalline water ice, not the dirty, darkened, carbon-rich ice that coats most trans-Neptunian objects. Clean, bright, crystalline water ice, a surface composition that is unusual for objects in the Kuiper Belt, where billions of years of cosmic radiation bombardment should have long since darkened and disordered the ice on any undisturbed surface. The fact that Haumea's ice remains bright and crystalline was the first hint that this body had been through something dramatic, something that the shape and rotation data would later confirm. But the truly bizarre signal was not the composition. It was the brightness variation. When astronomers monitored Haumea over time, plotting its brightness as it rotated, they found an extraordinary pattern. The light curve, the graph of brightness versus time, rose and fell in a smooth, repeating cycle with a period of roughly 3.9 hours. And the amplitude of that cycle was enormous. Haumea's brightness changed by roughly 30% over the course of a single rotation. At its brightest, it was reflecting nearly a third more light than at its faintest. For context, most solar system bodies show brightness variations of only a few percent during rotation. A slightly lumpy asteroid might vary by 5 or 10%. A planet with distinct surface markings might show a subtle rise and fall. A 30% swing in brightness is extraordinary for a body large enough to be a dwarf planet. And the explanation for it is what confirmed Haumea's extraordinary shape. There are, in principle, two ways a rotating body can show large brightness changes. The first is extreme surface variation. If one hemisphere is covered in bright, reflective material and the other in dark, absorptive material, the brightness will change as the body rotates and presents different faces to the observer. The second explanation is shape. If the body is elongated, the cross-sectional area presented to the observer changes as it turns. When the long axis faces toward you, you see a large projected area and the body looks bright. When the short axis faces toward you, you see a smaller area and the body looks dim. The larger the elongation, the larger the brightness change. For Haumea, every line of evidence points to shape as the dominant cause. Later thermal observations sealed it. When astronomers measured Haumea's heat emission at infrared wavelengths, they found that the thermal light curve tracked the visible light curve almost perfectly. When the visible brightness peaked, the thermal emission peaked. When the visible brightness dipped, the thermal emission dipped. This correlation means the temperature distribution on Haumea's surface follows its shape, not patchy surface markings. A body with one bright hemisphere and one dark hemisphere would show different thermal behavior. A body that is physically larger in one direction than another shows exactly the pattern Haumea displays. The implication is vivid. Every 3.9 hours, Haumea presents a completely different profile to any observer. From one angle, it shows its broadest cross-section, its elongated body stretched across the field of view. 2 hours later, It has turned far enough that the short axis faces the observer, and the body appears dramatically smaller. 2 hours after that, the long axis swings back around. The cycle repeats, endlessly, for billions of years. This world has been turning at this rate since whatever event set it spinning, showing one face and then another, over and over in the dark. The question that demands an answer is how? How did Haumea come to spin this fast? Every other known dwarf planet rotates at speeds comfortable enough that gravity maintains a nearly spherical shape. What made Haumea different? The rotation of a body in space does not change on its own. There is no friction in the vacuum of the outer solar system, no air resistance, no medium to slow a spinning object. Once a body is set rotating at a given rate, it maintains that rate indefinitely, unless an external torque acts on it. Tidal interactions can gradually alter rotation rates over very long timescales. The moon's gravity, for example, is slowly decelerating Earth's spin, adding roughly 1.4 milliseconds to the length of an Earth day every century. But Haumea has no massive neighbor close enough to exert meaningful tidal braking. Its two moons are far too small to make a difference. Neptune, its nearest giant planet, is too distant. The solar system's other large bodies are all further away still. Haumea's current rotation rate is, for all practical purposes, the rotation rate it has carried since the event that created it. And that event was not gentle. The angular momentum contained in Haumea's spin is immense. Angular momentum is a conserved quantity. It cannot be created from nothing. It must come from somewhere. For a body the size of Haumea to be rotating once every 3.9 hours, a staggering amount of rotational energy had to be delivered to it in a single event or a very small number of events early in its history. Slow processes, gradual accumulation, gentle nudges from passing objects, none of these can account for the magnitude of the spin. The only mechanism consistent with the physics is a major impact. A collision between two large bodies in the outer solar system, violent enough to merge or partially merge the impactors, strip away outer layers of material, and leave the resulting body spinning at a rate that it maintains to this day. We will return to that collision in detail. It is the key to everything that makes Haumea what it is. But for now, what matters is the consequence. A world that should be round is not round. The reason it is not round is that it was set spinning with such violence that rotation now competes with gravity as the dominant force shaping its body. And that competition is not a metaphor. It is a real, measurable, physical contest happening inside Haumea at this moment, as it has been happening for billions of years. Gravity pulls inward, trying to compress the body into a sphere. Rotation pushes outward at the equator, trying to stretch it. The result is a shape that reflects neither force alone, but the negotiated balance between them. At Haumea's surface, the temperature sits at approximately minus 241 degrees Celsius. At that temperature, water ice behaves like rock. It is rigid, brittle, and hard. But Haumea is not a small body. Its longest axis stretches to at least 2,322 kilometers, large enough to rank among the biggest objects in the Kuiper belt. Its mass is substantial enough that pressures deep inside the interior are significant. Under these pressures, even ice at these temperatures can deform slowly over geological timescales. It flows, not like water, not like anything you would recognize as flowing. But over millions and billions of years, the material responds to stress and moves, particle by particle, grain by grain, until the body has adjusted its shape to match the forces acting on it. This is the same principle that allows glaciers to flow on Earth, and the same principle that has allowed Haumea to settle into the elongated form we observe today. That form is not random. It is not accidental. It is the specific shape that minimizes the total energy of the system given Haumea's mass, composition, rotation rate, and internal structure. Physics predicts what that shape should be. For a slowly spinning body, the answer is a sphere or a slightly oblate spheroid, a shape flattened at the poles and widened at the equator, like a gently squished ball. But if the rotation exceeds a critical threshold, the equilibrium shape transitions from this oblate form into something more dramatic, a triaxial ellipsoid where all three axes have different lengths, and the body is visibly elongated along one direction. This shape was first described mathematically in the 1800s by the German mathematician Carl Gustav Jacobi, and it bears his name today, a Jacobi ellipsoid. Haumea appears to exist at or near this Jacobi regime. But when scientists tried to match the predicted Jacobi shape to the actual measurements of Haumea's body, something did not fit. The measured shape and the measured density did not produce a consistent solution when plugged into the equations for a uniform body in hydrostatic equilibrium. There was a gap between what the mathematics said a uniform, rapidly rotating body of Haumea's density should look like, and what Haumea actually looks like. That discrepancy is small in numerical terms, but enormous in its implications. It means Haumea is not simple. Its interior is not uniform. Something about its internal structure, the way mass is distributed between core and surface, rock and ice, dense interior and lighter shell, changes the way it responds to its own rotation. That internal structure is a window into the event that made Haumea what it is. And to see through it, we need to go deeper into the physics of what happens when a body this large spins this fast. We need to understand what the shape actually tells us about the material inside, and why the answer forces us to conclude that Haumea is not just oddly shaped, but fundamentally different from what it appears to be on the outside. The shape holds the answer, and the shape is stranger than it looks. In the 1830s, a mathematician named Carl Gustav Jacob Jacobi proved something remarkable about spinning fluid bodies. He showed that when a mass of self-gravitating fluid rotates fast enough, the expected flattened sphere is no longer the only stable shape. A second family of solutions opens up. The body can settle into a triaxial form, elongated along one axis, narrower along a second, shortest along the third, all three dimensions different from one another. This was a prediction rooted entirely in mathematics. No one had ever observed such a body in space. No telescope had ever revealed a world stretched into three unequal axes by its own rotation. The prediction sat in the theoretical literature for over a century, beautiful and largely abstract. Haumea turned that abstraction into a physical reality. To understand what Haumea's shape actually tells us, we need to follow the full sequence of what happens to a gravitating body as its rotation increases. The physics is not complicated in principle, but the consequences are extraordinary, because they describe a process by which rotation physically reshapes a world. Not metaphorically, not approximately. The body changes its geometry in response to the forces acting on it. The same way a lump of clay on a potter's wheel spreads outward as the wheel spins faster. Except in this case, the clay is a world more than 1,000 kilometers across, The wheel is its own angular momentum, and the process unfolds over geological time. Start with no rotation at all. A non-rotating body in hydrostatic equilibrium is a perfect sphere. Every point on the surface is exactly the same distance from the center. Gravity pulls inward with equal force in every direction, and the body has no reason to favor one axis over another. This is the simplest case. The sphere is the minimum energy shape for a non-spinning, self-gravitating fluid. Now add a small amount of rotation. The body begins to spin around an axis. At the equator, the rotation produces an outward centrifugal effect. Material at the equator experiences a combination of inward gravitational pull and outward rotational push. The net inward force at the equator is slightly less than at the poles, where no centrifugal effect operates. The body responds by spreading outward at the equator and contracting slightly at the poles. It becomes what mathematicians call a Maclaurin spheroid, named after the Scottish mathematician Colin Maclaurin, who first described this family of equilibrium shapes in the 1740s. The Maclaurin spheroid is oblate. It is wider at the equator than from pole to pole, but it is still axially symmetric. If you looked at it from directly above the pole, it would appear perfectly circular. Every cross-section through the equator is a circle. Only the vertical profile is flattened. This is the shape most planets in the solar system approximate. Earth is a Maclaurin spheroid. Jupiter, spinning once every 10 hours, is a noticeably more flattened one. Saturn, with its low density and rapid spin, is the most oblate planet, visibly squished even in a small telescope. All of them are axially symmetric. All of them are wider at the equator. None of them are elongated along any equatorial direction. The Maclaurin sequence handles them all, but there is a limit. As the rotation rate continues to increase, the Maclaurin spheroid becomes more and more oblate, more and more flattened, and at a specific critical ratio of rotational energy to gravitational energy. The mathematician Jacobi showed that the axially symmetric shape is no longer the only equilibrium option. A second branch of solutions appears. The body can break axial symmetry and adopt a shape where the equator itself is no longer circular. One equatorial axis becomes longer than the other. The body elongates. It transitions from a flattened disc-like form into something genuinely triaxial, stretched along one direction in the equatorial plane. This transition is called the Jacobi bifurcation, and once a body crosses it, the resulting equilibrium shape is the Jacobi ellipsoid. The transition is not violent. It is not a sudden snap from one shape to another. In a fluid body, it happens gradually as conditions change, but the consequence is dramatic. A body that was symmetric around its rotation axis, looking the same from every direction when viewed from above the pole, transforms into a body that is visibly elongated, presenting a completely different profile depending on which direction you view it from in the equatorial plane. This is where Haumea lives. Its rotation rate, its mass, and its internal properties place it in the regime where the Jacobi sequence applies. Gravity has not given up. Haumea is not flying apart. It is not unstable. It is not approaching destruction. It is in equilibrium. But the equilibrium it has found is not a sphere. It is not even a flattened sphere. It is a triaxial body, stretched along its longest axis by the outward push of its own rotation, compressed along its shortest axis by the inward pull of its own gravity. And the mathematics of this equilibrium makes a very specific prediction. For a body of uniform density rotating at a known rate, The three axes of the Jacobi ellipsoid are completely determined. You do not get to choose them independently. Given the rotation rate and the density, the ratios between the axes are fixed. This means that measuring the shape of the body tells you its density, and measuring its density tells you its shape. They are locked together by the physics. This is what made the 2017 stellar occultation so important and so disruptive. A stellar occultation is one of the most powerful tools available for measuring the size and shape of distant solar system objects. The principle is direct. When a small body passes in front of a distant star as seen from Earth, it blocks the starlight. The shadow of that body sweeps across Earth's surface. If multiple telescopes are positioned along the shadow path, each one records the moment the starlight disappears and the moment it returns. The duration of the disappearance at each site gives the length of the chord, the slice of the body's outline that the telescope's line of sight crossed. Combine enough chords from enough sites, and you can reconstruct the projected shape of the body at the instant the occultation occurred. On January 21st, 2017, Haumea passed in front of a faint background star. The event had been predicted months in advance. Ortiz and a team of more than 50 collaborators from institutions across Europe coordinated observations from 10 observatories in 6 countries. The telescopes were positioned along the predicted shadow path, each one recording precise timestamps as the starlight vanished and reappeared. When the data was compiled, the result was a set of chords that traced the outline of Haumea at that moment in its rotation. The projected shape was an ellipse, as expected. The semi-major axis of that projected ellipse measured approximately 852 kilometers. The semi-minor axis measured approximately 569 kilometers. Combined with the known rotation period and the orientation of Haumea's spin axis, these measurements constrain the full three-dimensional shape. The longest semi-axis came out to approximately 1,161 kilometers. The intermediate axis to roughly 852 kilometers. The shortest axis to roughly 523 kilometers. These numbers were substantially larger than previous estimates based on light curve modeling and thermal emission data. Earlier studies had suggested semi-axes of approximately 960 by 774 by 513 kilometers. The occultation showed that Haumea was bigger than anyone had thought. Its longest full axis stretched to at least 2,322 kilometers, a dimension comparable to Pluto's diameter. And that larger size changed everything about the density calculation. Density is mass divided by volume. Haumea's mass had been well constrained by the orbits of its moons, measured at roughly 4 × 10 to the 21st kilograms. That mass was not in question. But the volume depends on the size of the body, and volume scales with the cube of the dimensions. A modest increase in each axis produces a large increase in the total volume. The previous smaller size estimates had yielded a density of roughly 2,600 kilograms per cubic meter, which is notably high. Denser than most other known trans-Neptunian objects, and closer to the density of rock than to the density of ice. That high density had been one of Haumea's defining characteristics. It suggested a body dominated by rock, with only a thin veneer of ice on the surface, quite different from objects like Pluto or Eris, which have lower densities consistent with a roughly even mixture of rock and ice. The occultation's larger dimensions pushed the volume upward and the calculated density downward. The revised upper limit for the density came to approximately 1,885 kilograms per cubic meter, dramatically lower than the old value. This new figure was much closer to the densities of other large trans-Neptunian objects, closer to Pluto's density of roughly 1,854 kilograms per cubic meter, and more consistent with a body containing a substantial fraction of ice, in addition to rock. That shift in density was not just a bookkeeping correction. It broke the simple Jacobi model. For a uniform body, a single density and a single rotation rate produce a single set of axis ratios. The old, higher density had been consistent with a uniform Jacobi ellipsoid. The shape predicted by the Jacobi equations for a body of that density spinning at Haumea's rate matched the old, smaller size estimates reasonably well. The story was tidy. Haumea was a dense, rocky body with a thin ice layer, spinning fast enough to adopt a Jacobi shape. Everything fit. The new, lower density did not fit. When the Jacobi equations were fed the revised density and the known rotation rate, the predicted axis ratios did not match the observed shape. The measured Haumea was too elongated for its density if it were a uniform body in hydrostatic equilibrium. Something about the simple model was wrong. There were two possible explanations. Either Haumea is not in hydrostatic equilibrium at all, meaning its shape is partly supported by the rigid strength of its materials rather than by fluid-like flow, or Haumea is in hydrostatic equilibrium but is not uniform. It has internal structure, layers, a denser interior, and a lighter exterior arranged in a way that changes the mathematics of the equilibrium shape. The first option would be unusual for a body of Haumea's size. Objects larger than a few hundred kilometers in diameter are generally expected to have internal pressures high enough to overcome the rigid strength of rock and ice over geological time. Their interiors deform. They flow, they reach equilibrium. Invoking rigid body support for a body more than 2,000 kilometers along its longest axis would require special circumstances. Perhaps an unusually cold and rigid interior, or a body that has not yet had time to relax into equilibrium after a recent disruption. Neither of those explanations is impossible, but neither is the simplest interpretation. The second option is more natural, and it resolved the discrepancy elegantly. In 2019, a team led by Emily Dunham at the University of Arizona tackled this problem head-on. They wrote a computational code to calculate the equilibrium shape of a rapidly rotating, differentiated body, meaning a body with an internal structure consisting of a denser core surrounded by a lighter mantle. When they imposed the known rotation rate and explored a range of internal structures, they found entire families of solutions where a differentiated Haumea could exist in hydrostatic equilibrium, with dimensions matching the occultation measurements. Their preferred solution described a body with semi-axes of approximately 1,050 by 840 by 537 kilometers and a bulk density of roughly 2,018 kilograms per cubic meter. The interior consisted of a dense, rocky core surrounded by a thick shell of water ice. The core comprised a large fraction of the total volume. The ice mantle was not a thin veneer. It was a substantial layer, hundreds of kilometers thick, wrapping the denser interior. This structure makes physical sense. Haumea is large enough and was likely warm enough in its early history for differentiation to have occurred. When a body of mixed rock and ice experiences sufficient internal heating, whether from the energy of its formation, from radioactive decay of elements in its rocky component, or from the violence of a major impact. The denser, rocky material sinks toward the center, and the lighter ice rises toward the surface. The body separates into layers, the way oil and water separate in a jar when shaken and then left to settle. Once this differentiation occurs, the body's response to rotation changes. A layered interior distributes mass differently from a uniform one. The denser core, concentrated near the center, allows the lighter outer shell to extend further outward without violating the constraints of equilibrium. The body can be larger and more elongated at a given density than a uniform body of the same total mass. This is the resolution. Haumea is not a uniform lump of mixed rock and ice that has been stretched by rotation. It is a differentiated world with a rocky heart and an icy exterior, and the interaction between that internal layering and its extreme rotation produces the shape we observe. The simple Jacobi model was not wrong in its physics. It was wrong in its assumption that Haumea is uniform. Once differentiation is accounted for, the shape, the density, the rotation rate, and the measured dimensions all converge on a consistent picture. But the story did not end there. In early 2026, a team led by Clement Stay-Len published a study that pushed the physics further than anyone had gone before. Using a specialized code called Balinese, designed to compute equilibrium figures for multi-layered rotating bodies, they explored what happens when a differentiated Haumea approaches the absolute limit of rotational stability. And what they found was startling. For certain plausible interior models, the equilibrium shape closest to the one derived from the 2017 occultation sites near a state of critical rotation. Critical rotation is the threshold beyond which no stable equilibrium exists. Spin a body faster than this limit, and it will begin to shed mass from its equator. Material at the tips of the longest axis, where the combined effect of rotation and elongation produces the weakest net gravitational binding, will be flung outward. The body will lose material until it slows enough to restabilize. Haumea may not have crossed that line. It is not actively flying apart. But Stay-Len and colleagues showed that if Haumea sits very close to the critical threshold, its equilibrium shape would not be a smooth ellipsoid at all. Instead, it would be pinched. The tips of the longest axis would narrow inward, deviating from the smooth ellipsoidal profile by as much as 110 kilometers. The body would have a waist, a subtle narrowing at the ends of its most extended dimension, as if the equatorial tips were being squeezed by the competing forces of gravity pulling inward and rotation pushing outward. This pinch shape cannot be distinguished from a smooth ellipsoid using the 2017 occultation data. The geometry of that event, the angle at which Haumea's shadow crossed the observing stations, did not sample the regions of the body where the pinching would be visible. But the researchers calculated that a future stellar occultation, predicted for May 4, 2026, would occur at a rotational phase where Haumea's longest axis is nearly face onto the observer. At that orientation, chords crossing the northern and southern limbs of the shadow could, in principle, reveal whether the body's outline deviates from a smooth ellipse. If the pinch shape is real, and if observations detect it, it would confirm that Haumea is not merely near critical rotation, but right at the edge of it. A world on the verge of losing material from its own equator because it spins so fast that gravity can barely hold on. That possibility connects directly to one of the proposed scenarios for how Haumea's collisional family formed. If Haumea was once spinning even faster than it does today, it may have shed icy material from its equatorial tips through rotational fission, rather than through a single catastrophic impact. The fragments ejected from the equator would carry the surface ice composition, explaining why the family members all share Haumea's distinctive water ice spectral signature. The pinch shape, if confirmed, would be physical evidence that this process is not merely plausible, but written into the geometry of the body itself. The composition of Haumea's surface adds another layer to this picture. The crystalline water ice that dominates the surface is not what you would naively expect to find on a body in the Kuiper belt. At the temperatures that prevail at 43 astronomical units from the Sun, roughly minus 241 degrees Celsius, water ice should exist in an amorphous form. Amorphous ice lacks the regular, repeating molecular structure of crystalline ice. It is disordered, glassy, the default state of ice that has been bombarded by cosmic radiation for billions of years, without any energy input to reorganize its structure. The fact that Haumea's surface shows crystalline rather than amorphous ice means something has refreshed that surface. Either internal heat, perhaps residual warmth from a past collision, or from tidal interactions, has periodically warmed the surface enough to allow the ice to anneal into its crystalline form. Or the surface itself is geologically young, exposed relatively recently by an event that stripped away the older, radiation-darkened, amorphous outer layer. Both explanations point toward a history of disruption. A body that has sat undisturbed in the Kuiper belt for 4.5 billion years should have a dark, irradiated, amorphous surface. Haumea does not. Its surface is bright, reflective, and crystalline. Something happened to it. Something that either continues to supply energy to the surface, or that exposed fresh material from the interior within the cosmically recent past. There is additional evidence on the surface itself. Photometric observations have revealed a feature informally called the dark red spot, a region on Haumea's surface that is noticeably darker and redder than the surrounding bright white ice. The spot's properties are consistent with a region where a different material has been exposed, perhaps a patch of the rocky interior revealed by an impact that punched through the icy outer layer. If this interpretation is correct, the dark red spot is a window into Haumea's interior, a place where the icy shell was breached and the denser material beneath was laid bare. It would be direct visual evidence that the bright ice we see is not the whole story, that beneath the frozen surface lies the rocky core that the equilibrium models predict. The albedo itself tells a similar story. Haumea reflects approximately 51% of the sunlight that reaches it, a geometric albedo of roughly 0.51. This is high for a Kuiper belt object, where albedos of 5 to 15% are more typical. Most trans-Neptunian surfaces are dark, coated in tholins, complex organic compounds produced when simple molecules like methane and nitrogen are irradiated by ultraviolet light and cosmic rays over billions of years. These tholins give many Kuiper belt objects their characteristic reddish-brown coloring and low reflectivity. Haumea's bright, clean ice surface stands in stark contrast. It is as if the dark organic coating that should have accumulated over billions of years has been removed or has never had time to form. This is consistent with a surface that was stripped, or refreshed by a major event. A collision violent enough to spin Haumea to its current rate would have been violent enough to blast away the outer layers of irradiated, darkened material, exposing fresh ice from the interior. The crystalline structure of that ice, the high albedo, and the anomalous surface composition all point in the same direction. Haumea's exterior is not the original surface of a body that formed 4.5 billion years ago, and has sat undisturbed ever since. It is the aftermath of something that happened later. Something energetic enough to reshape the surface while leaving the deeper structure intact. All of these lines of evidence, the shape, the density, the internal layering, the rotation rate, the surface ice, the albedo, the dark red spot, converge on a single narrative. Haumea is a differentiated body, rocky inside and icy outside, spinning so fast that its own rotation has pulled it into a dramatically elongated equilibrium shape that may approach the very limit of rotational stability. Its surface shows the signs of a violent past. Material that has been stripped, refreshed, or exposed by forces far more dramatic than the quiet radiation, weathering that dominates most Kuiper Belt surfaces. And the mathematics of its shape, when worked out in full detail, suggests a body that is not simply spinning fast, but is spinning near the fastest rate at which it could hold together at all. That is what the shape tells us. A world in balance. A balance between the inward pull of its own gravity and the outward push of its own spin, negotiated over billions of years, locked into a geometry that encodes the violence of its origin in every curve and dimension of its body. Not an oddity, not an accident. A physical record of forces that have been at work since before the solar system looked anything like it does today. But Haumea's shape is only part of the picture. This world does not sit alone in the darkness. Orbiting around it, held in place by the same gravity that fights its rotation, are two moons and a ring, each one carrying its own set of clues. And when you look at what they reveal about the system as a whole, the story becomes stranger and more precise at the same time. Because the moons, the ring, the spin, and the shape do not just coexist, they are geometrically aligned, physically coordinated, connected by relationships that cannot be coincidence, relationships that demand a single, shared explanation. That explanation starts with what was found circling Haumea in the dark. In 2005, astronomers using the Keck Observatory's adaptive optic system on Mauna Kea, Hawaii, spotted a faint point of light moving alongside Haumea. It was small, dim, barely distinguishable from the background noise. But it was not a background star. It was not a detector artifact. It moved with Haumea, maintaining a fixed gravitational relationship over weeks and months of follow-up observation. The team, led by Mike Brown and his Caltech colleagues, had found a moon. A few months later, they found a second one. The larger and more distant of the two was named Hi'iaka, after the Hawaiian goddess of the island of Hawaii and of hula dancers, a daughter of the goddess Haumea in Polynesian mythology. The smaller and closer moon was named Na'maka, after a water spirit in the same mythological tradition, another daughter of the goddess. Together with their parent body, these two moons form a miniature system orbiting in the frozen darkness of the Kuiper Belt, more than 40 astronomical units from the Sun, a system whose properties would turn out to be as unusual and revealing as Haumea itself. Hi'iaka is the larger moon. Its estimated diameter is roughly 310 kilometers, making it one of the largest known satellites of any Kuiper Belt object. It orbits Haumea at a substantial distance, completing one revolution approximately every 49 Earth days. Its orbit is nearly circular, with low eccentricity, and it moves in a plane closely aligned with Haumea's equator. Spectroscopic observations reveal that Hi'iaka's surface, like Haumea's, is covered in nearly pure crystalline water ice. The absorption features in its near-infrared spectrum are deep, clean, and unmistakable. Whatever Haumea's surface is made of, Hi'iaka's surface matches it almost exactly. That similarity is not trivial. In the outer solar system, where surfaces are chemically diverse, sculpted by billions of years of radiation processing, micrometeorite bombardment, and varying initial compositions, finding a moon whose surface is spectroscopically indistinguishable from its parent body is a powerful clue. It means the two objects share a common origin. The ice on Hi'iaka did not arrive from somewhere else. It came from the same source that produced Haumea's own icy exterior. The implication is that Hi'iaka was born from Haumea, carved out of it by whatever event set the system in motion. There is another detail about Hi'iaka that deepens this connection. It rotates quickly. Observations of its own light curve reveal a rotation period of roughly 9.8 hours. That is fast for a moon of its size. Most small icy bodies in the outer solar system rotate much more slowly. A fast-spinning moon orbiting a fast-spinning primary, both covered in the same composition of crystalline water ice, both existing in the same orbital plane, all of this points toward a system that was forged in a single event, rather than assembled piecemeal over time through captures and chance encounters. Haumea is the smaller inner moon. Its estimated diameter is roughly 170 kilometers. Though this figure carries significant uncertainty due to the difficulty of separating its faint light from Haumea's glare at such enormous distances. Haumea orbits closer to Haumea than Hi'iaka, completing one revolution in approximately 18 Earth days. Its orbit, however, tells a more complicated story than its siblings. Where Hi'iaka follows a calm, nearly circular path, Haumea's orbit is noticeably more eccentric and dynamically complex. Its orbital plane is slightly inclined relative to Hi'iaka's, and its motion shows the gravitational influence of multiple forces acting simultaneously. Haumea's elongated shape generates a gravitational field that is not spherically symmetric. A perfectly round body pulls equally in all directions. An elongated body does not. The gravitational field of a triaxial body has harmonics, variations in strength that depend on direction and distance, and these harmonics perturb the orbits of any nearby objects. Haumea, orbiting closer to Haumea than Hi'iaka, feels these perturbations more strongly. Its orbit wobbles. It precesses. It responds to the fact that the body it orbits is not round. This interaction between Haumea's orbit and Haumea's shape is scientifically valuable precisely because it is complex. The orbital perturbations depend on Haumea's gravitational harmonics, which in turn depend on how mass is distributed inside the body. By tracking the exact motion of the moons over time, astronomers can work backward to infer properties of Haumea's interior that no telescope can image directly. The shape of the gravitational field encodes the shape of the internal structure. Dynamical studies of the two moons have revealed additional complexity. Research published by Matija Chuk, Darin Ragozin and David Nezvorny found that the current orbits of He-Iakar and Namakar are consistent with a past orbital resonance between the two moons. At some point in their history, the moon's orbital periods fell into a ratio where gravitational interactions between them became amplified, pumping up eccentricities and inclinations in a pattern that matches the current orbital state. The researchers concluded that the moons likely formed in a flat disk close to their present locations, possibly as second-generation bodies assembled from debris left over after a larger, earlier moon was destroyed. This scenario, in which a single large initial moon forms from a collision, evolves tidally outward, and is then disrupted to create the current pair of smaller moons, has become one of the leading frameworks for understanding the Haumea system. The orbital geometry of the moons carries one more piece of critical information. Both moons orbit in planes that are closely aligned with Haumea's equator. This is significant because there is no dynamical reason for captured objects to share Haumea's equatorial plane. If the moons have been wandering Kuiper Belt objects that happen to drift close enough to be captured by Haumea's gravity, their orbits would show random orientations, tilted at arbitrary angles to the equator. They do not. They orbit in the plane you would expect if they had formed from a disk of debris orbiting around Haumea's equatorial region. That disk could only have been produced by an event that ejected material from Haumea itself, material that settled into the equatorial plane under the combined influence of Haumea's gravity and rotation, before coalescing into the moons we observe today. 2 moons, both icy, both orbiting in Haumea's equatorial plane, both showing signs of a shared violent origin. The system was already extraordinary. And then, in 2017, it became something else entirely. When the stellar occultation of January 21st, 2017 was analyzed, the primary target was Haumea's shape and size. Those results, the revised dimensions, the lower density, the constraints on the triaxial figure, dominated the scientific discussion. But the occultation data contained a second discovery, one that nobody had expected. As Haumea's shadow swept across the European observing sites, several telescopes recorded brief, shallow dips in the starlight that occurred before and after the main occultation event. These secondary dips were not caused by the body of Haumea itself. They were too far from the main shadow, separated by thousands of kilometers from the limb of the dwarf planet. And they were too brief, lasting only fractions of a second, consistent with a narrow structure rather than a large solid body. The team, led by Ortiz and including more than 50 collaborators, analyzed these secondary events and reached a conclusion that shocked the planetary science community. Haumea has a ring. The ring has a radius of approximately 2,287 kilometers, measured from the center of Haumea's body. It has a width of roughly 70 kilometers and an opacity of approximately 0.5, meaning it blocks about half the light that passes through it. It is not a thick, bright, easily visible structure like the rings of Saturn. It is narrow, relatively faint, and detectable only through the precise photometric methods that stellar occultations provide. But it is real. Multiple observing sites recorded the secondary dips, and the timing and geometry of those dips are consistent with a single, coherent ring encircling the dwarf planet. The existence of a ring around a body like Haumea raises questions that go beyond discovery alone. Rings are fragile structures. They are collections of small particles, each one independently orbiting the central body, maintained in a coherent band only as long as the forces acting on them remain in balance. Around a spherical planet, the physics of ring stability is well understood. Gravity from the central body, the orbital velocity of the particles, and the occasional gentle collisions between them produce a system that can persist for millions or even billions of years under the right conditions. Around Haumea, the situation is fundamentally different. The central body is not spherical. It is a rapidly rotating triaxial ellipsoid whose gravitational field is correspondingly non-uniform. A ring particle orbiting Haumea does not feel a constant smooth gravitational pull. It feels a field that varies in strength and direction as the elongated body beneath it rotates. Every 3.9 hours, the gravitational landscape shifts. The long axis swings toward the particle, then away. The gravitational tug strengthens, then weakens in a repeating cycle that applies periodic torques to the particle's orbit. For most orbital distances, these periodic torques are destabilizing. They pump energy into the particle's orbit, gradually nudging it away from its original path until it either collides with Haumea, gets ejected from the system, or migrates to a different orbital distance. The fact that a ring survives at all in this environment means the particles have found an orbital niche where the destabilizing effects cancel out. Only at very specific orbital distances do the gravitational kicks cancel themselves out, arriving in a sequence whose cumulative effect over many cycles sums to zero. At those distances, and only at those distances, ring particles can survive indefinitely. Everywhere else, the elongated body's rotating field clears the orbit. The ring exists because its particles have found one of the narrow, safe corridors in a gravitational environment that would destroy them anywhere else. To appreciate how unexpected this discovery was, consider the context. Before 2013, rings were known only around the 4 giant planets: Jupiter, Saturn, Uranus, and Neptune. These are enormous worlds with powerful gravitational fields and complex satellite systems. The idea that a small body in the outer solar system could possess a ring seemed implausible. Then, in 2013, astronomers observed a stellar occultation by the Centaur object Rik-Lo, a small icy body orbiting between Jupiter and Neptune, and found not 1 but 2 narrow, dense rings encircling it. That discovery was revolutionary. It demonstrated that rings are not exclusive to giant planets. Small bodies can have them too. The Centaur Chiron was subsequently found to possess features consistent with a ring or ring-like structure, and in 2023, the trans-Neptunian object Quaoar was confirmed to have a ring at an unusually large distance from its surface. But Haumea's ring, announced in October 2017, made the dwarf planet the first trans-Neptunian object ever confirmed to host a ring system. It was also the most distant ringed body known at the time of discovery. The Kuiper Belt, already home to the strangest dwarf planet in the solar system, now contained the most distant known ring as well. What makes Haumea's ring scientifically remarkable is not simply that it exists. It is where it sits and what that location tells us about the physics of the system. The ring's orbital radius of approximately 2,287 kilometers places it close to what is called the 3-to-1 mean motion resonance with Haumea's spin period. This means that in the time Haumea completes 3 full rotations on its axis, a particle in the ring completes approximately 1 full orbit around the body. 3 spins of Haumea for every one orbit of a ring particle. This is the safe corridor described earlier. The 3-to-1 resonance is the specific orbital distance, where the periodic gravitational perturbations from Haumea's rotating elongated body cancel out over time, allowing ring particles to persist in stable orbits rather than being scattered or driven into the surface. There is a deeper connection still. The ring is coplanar with Haumea's equator. It lies in the same geometric plane as the equatorial bulge of the elongated body. And it is also coplanar with the orbit of Haumea. The equator, the ring, and the outer moon's orbital plane are all aligned. 3 independently measurable orientations in 3-dimensional space, all pointing the same direction. The probability of this alignment occurring by chance is vanishingly small. It is a signature of a system that was shaped by a single organizing event, one that established the equatorial plane as the preferred plane for everything that orbits Haumea. This alignment connects back to the formation scenario. If a collision or rotational event ejected material from Haumea's equatorial region, that material would naturally settle into the equatorial plane. Some of it would coalesce into moons. Some of it would remain as debris, forming a disk or ring. The ring we see today may be a remnant of that original debris disk, maintained in its current configuration by the 3-to-1 resonance with Haumea's spin. Or it may be a younger structure, produced by a more recent disruption of a small satellite, or by ongoing processes that we do not yet fully understand. The origin of the ring itself remains an open question, but its geometry is not ambiguous. It belongs to the same system, governed by the same physics, aligned with the same plane as everything else that orbits Haumea. Since 2017, new observations have continued to refine our understanding of this system, and recent years have produced developments that bring the story closer to resolution. In March 2025, a team led by Estela Fernandez Valenzuela observed a stellar occultation using NASA's infrared telescope facility on Mauna Kea. The target was ambitious. The team was not merely watching for Haumea's shadow. They were attempting to detect the shadow of Namaka, the smaller and closer moon, during the same event. Detecting the shadow of a moon estimated at roughly 170 kilometers in diameter, orbiting a body more than 43 astronomical units away, required extraordinarily precise predictions, careful timing, and favorable geometry. They succeeded. The light curve recorded at the infrared telescope facility showed 2 distinct dropouts, one from Haumea's body and one from Namaka. The timing difference between the predicted and observed positions of Namaka was only 0.7 plus or minus 0.2 seconds, a validation of the orbital model that had been constructed from years of patient astrometric work. The single chord across Namaka's shadow placed a lower limit of 83 plus or minus 2 kilometers on its diameter. A single chord cannot determine the full shape or size of a body, but it establishes a floor. Namaka is at least 83 kilometers across, and likely larger. What the occultation cannot yet determine from a single chord is Namaka's full 3-dimensional shape or its density, but the lower limit on its size, combined with existing estimates of its mass derived from orbital dynamics, begins to constrain the possibilities. If Namaka turns out to be significantly larger than 83 kilometers, its calculated density would drop below what solid water ice would produce, suggesting a porous interior, a loosely packed body rather than a solid one. A porous structure would be consistent with a moon that assembled gradually from orbiting debris rather than one that formed as a single intact fragment. Rubble reassembles loosely. It does not compact into a dense, coherent mass without additional forces, sustained internal heating, or high-velocity secondary impacts that drive the material together. A low-density, porous namakhar would strengthen the case that both moons coalesced from a debris disk rather than being chipped off Haumea as solid chunks. It would also provide a physical basis for understanding why Namakhar's orbit is dynamically more complex than its siblings. A porous body responds differently to tidal forces than a rigid one. Its internal friction is higher. Its tidal dissipation is stronger. These properties affect how quickly and in what direction its orbit evolves over geological time, adding another measurable constraint to the history of the entire system. This detection was only the second time a satellite in the Haumea system had been directly measured through a stellar occultation. The first was Haumea, observed during two separate stellar occultation events in 2021 by a team led by Fernández Valenzuela. Together, these detections of both moons through independent occultation events open a new chapter in the study of the Haumea system. By combining the occultation-derived positions and sizes of both moons with their orbital dynamics, researchers can now attempt to independently measure the masses of Haumea and Namakhar, and, crucially, to measure Haumea's gravitational harmonics. Gravitational harmonics are the mathematical terms that describe how a body's gravitational field deviates from that of a perfect sphere. For a spherical body, the gravitational field depends only on mass and distance. For a non-spherical body, additional terms enter the equation, each one encoding information about how mass is distributed inside the body. The most important of these for Haumea is the term known as J2, the quadrupole moment, which describes how much the gravitational field deviates from spherical symmetry due to the body's elongated shape. Here is why this matters. Haumea's shape has been measured from the outside through occultations and light curves. Its internal structure has been modeled computationally, but the gravitational harmonics provide a direct, independent probe of the interior. If the shape is known from occultations and the gravitational field is known from the moon's orbits, combining the two constrains the density profile inside the body. A geophysical model published by Dunham and colleagues in 2019 predicted that a differentiated Haumea with a hydrated rocky core comprising roughly 83% of the body's volume would produce a J2 value of approximately 0.16. If future orbital analysis of the moons yields a J2 measurement, it can be compared directly to this prediction. Agreement would confirm the differentiated structure. Disagreement would force a revision. This is the promise of the ongoing observational campaign. Every stellar occultation, every refined orbital measurement, every new data point on the moon's positions tightens the constraints on what Haumea looks like on the inside. The exterior has been mapped, the interior is being probed, and the two are converging toward a single coherent picture. The most anticipated event in this campaign was the stellar occultation predicted for May 4, 2026. A paper published in early 2026 by Ortiz and collaborators analyzed this event in detail. They calculated that Haumea's shadow would be approximately 2,224 plus or minus 30 kilometers wide at the time of the occultation, far larger than the conservative nominal estimate of 1,380 kilometers that had been used for initial planning. The reason for the larger shadow was Haumea's rotational phase. At the moment of the occultation, Haumea would be oriented with its longest axis nearly face-on to the observer, only about 25 degrees from its maximum brightness phase. This meant the widest possible cross-section of the body would be presented, maximizing the shadow width and making the event detectable with relatively small telescopes. The occultation star was bright by the standards of these events. With a Gaia magnitude of 14.7, more than 3 magnitudes brighter than the star occulted in the 2017 event. Brighter stars produce sharper, more easily detected signals, allowing smaller observatories to participate. The shadow track was predicted to cross 3 continents, providing geographic diversity that reduced the risk of total cloud out at all sites. The event was, by every metric, the most favorable Haumea occultation opportunity in at least a decade. The scientific stakes extended beyond simply remeasuring Haumea's size. The 2026 study by Stalin and colleagues had predicted that if Haumea is near critical rotation, its equilibrium shape may deviate from a smooth ellipsoid. The tips of the longest axis could be pinched inward, narrowed by the competing forces of gravity and rotation near the limit of stability. This pinching, potentially amounting to deviations of up to 110 kilometers from a smooth ellipsoidal profile, would be most visible precisely at the rotational phase expected during the May 2026 event. Observers positioned to record chords crossing the northern and southern limbs of the shadow would be in the best position to detect whether Haumea's outline is truly elliptical or subtly pinched. A confirmed pinch shape would have profound implications. It would support the hypothesis that Haumea is a body in hydrostatic equilibrium, sitting at or very near the critical rotation rate. It would confirm that the 3-layer differentiated models are on the right track, and it would lend weight to the scenario in which Haumea's collisional family was formed, not by a single catastrophic impact, but by rotational mass shedding, a process in which material is flung from the equatorial tips of a body, spinning so fast that gravity can no longer contain it. The fragments shed from the equator would carry the surface ice composition, naturally explaining why the family members share Haumea's distinctive spectral signature. There is one more layer to the observational picture that connects the ring, the moons, and the shape into a single, tightly woven system. The ring's 3-to-1 resonance with Haumea's spin is not a static relationship. It depends on Haumea's rotation rate. If the rotation rate changes, even slightly, the resonance location shifts. The fact that the ring sits precisely at this resonance today means that the rotation rate has been stable enough, for long enough, to maintain the resonance. This is a constraint on any formation model. Whatever event created the ring must have done so after Haumea's rotation rate had settled to approximately its current value. If the ring were older than the current spin rate, it would not be at the resonance. If the spin rate had changed significantly since the ring formed, the ring would have dispersed or migrated. This stability constraint is another thread connecting the ring to the collision history. If a major impact set Haumea's spin billions of years ago, and the spin has been essentially constant since then, the ring could, in principle, be very old, maintained at the resonance for the full duration. Alternatively, the ring could be relatively young, formed from a more recent disruption of a small satellite, or from ongoing processes in the Haumea system, and simply happened to form near the resonance because that is where orbital dynamics naturally concentrate material. Both scenarios are under active investigation. Numerical simulations of ring formation around rapidly rotating triaxial bodies have explored how debris behaves in the complex gravitational environment surrounding an elongated object. These simulations confirm that only a small number of orbital distances permit long-term survival, and the 3-to-1 resonance is consistently among them. Material that begins at other distances is swept away within thousands of orbital periods, while material near the resonance persists, gradually concentrating into the narrow band that matches the observed ring. Step back now and consider what the full system looks like. At the center is Haumea itself, a triaxial body stretched along one axis to more than 2,322 kilometers, spinning once every 3.9 hours, its surface covered in bright crystalline water ice, its interior likely differentiated into a rocky core and an icy mantle, its shape possibly approaching the very limit of rotational stability. Around it orbits a ring, narrow, 70 kilometers wide, sitting at a radius of 2,287 kilometers, locked in a 3-to-1 resonance with the spin of the body it encircles, coplanar with the equator. Beyond the ring, 2 moons. Namaka, the smaller and closer, at least 83 kilometers across, orbiting in roughly 18 days, its path perturbed by the gravitational harmonics of its elongated parent. And Hi'iaka, the larger and more distant, roughly 310 kilometers in diameter, orbiting every 49 days, its surface spectrally identical to Haumea's, its own rotation unusually fast for a body its size. Everything orbits in the same plane. Everything shares the same composition. Everything is geometrically aligned. The ring, the moons, the equator, all locked into a single, coherent orientation in 3-dimensional space. This is not a system that was assembled by accident. It was not built by capture. It was not arranged by coincidence. The alignment, the shared composition, the dynamical relationships, all of them demand a common origin. One event, one moment in the deep past of the outer solar system when something happened to Haumea that was violent enough to set it spinning at its current rate, strip material from its body, eject that material into equatorial orbit, and leave behind the system of moons, ring, and elongated parent body that we observe today. And the evidence for that event does not end at the boundary of Haumea's gravitational influence. It extends outward into the Kuiper belt itself, where a scattered family of icy objects shares Haumea's orbit, Haumea's composition, and Haumea's spectral fingerprint. These objects are not orbiting Haumea. They are independent bodies, following their own paths around the sun, spread across a region of the Kuiper belt that spans millions of kilometers. But their orbits cluster together, their surfaces match. Their existence demands the same explanation that the moons and ring demand. Something happened to Haumea. Something that left marks not just on the body itself, not just on its immediate companions, but on the entire surrounding region of the Kuiper belt. And the nature of that event, the violence it required, the mechanisms it involved, and the story it tells about the early history of the outer solar system, is where this story has been heading from the beginning. In the asteroid belt between Mars and Jupiter, families are common. A large asteroid gets struck by a smaller one. The impact shatters the target or gouges out a chunk of its body. Fragments scatter outward along similar orbits, gradually spreading apart over millions of years, but retaining enough of a shared trajectory that astronomers can trace them back to a common origin, Dozens of these collisional families have been identified among the asteroids. They are a normal part of how small body populations evolve. Smash something, scatter the pieces, and the orbital fingerprint of the event persists for eons. In the Kuiper Belt, no such families were known until 2007. The outer solar system was assumed to be too sparsely populated, too cold, too slow for the kinds of energetic collisions that produce families among the asteroids. The velocities are lower, the distances between objects are greater. The probability of two large bodies meeting at the right speed and angle to produce a recognizable family was calculated to be vanishingly small. Then Mike Brown, along with Christina Barkume, Darin Ragozin, and Emily Schaller, published a paper in the journal Nature that changed that picture entirely. They announced the discovery of a group of Kuiper Belt objects, whose orbits clustered together in a way that was too tight to be coincidental. More strikingly, their surfaces all displayed the same unusual spectral signature: deep water ice absorption features and neutral colors, matching the surface of Haumea almost exactly. The objects were not orbiting Haumea. They were independent bodies on their own paths around the sun, but their orbits and their compositions linked them to each other and to Haumea with a specificity that demanded a shared origin. This was the Haumea collisional family, the first, and to this day, the only confirmed collisional family in the entire Kuiper Belt. The initial list of confirmed family members included roughly 10 objects, among them bodies designated 1995 SM55, 2002 TX300, and 2003 OP32. Each shares Haumea's distinctive spectral fingerprint. Each follows an orbit in the same general region of the Kuiper Belt, and each, when its trajectory is traced backward through dynamical models, converges toward a common origin point, consistent with a single disruptive event. The total mass of the known family members, excluding Haumea itself and its moons, adds up to roughly 2 to 5% of Haumea's current mass. These are not enormous objects. Most are a few hundred kilometers across at most, but they are numerous enough and compositionally distinctive enough to constitute a recognizable population, a cloud of icy debris scattered across the Kuiper Belt by whatever force created the Haumea system. And this is where the mystery begins, because the details of the family do not fit the simplest explanation. In the asteroid belt, collisional families form through catastrophic disruption. A high-speed impact shatters the target body, and fragments fly outward in all directions at velocities that exceed the escape velocity of the target. The fragments spread out over time but retain a detectable clustering in orbital space. The velocity dispersion among family members, the spread in their speeds relative to each other, is typically comparable to or larger than the escape velocity from the surface of the parent body. The Haumea family does not follow this pattern. The velocity dispersion among its members is roughly 140 meters per second. Haumea's escape velocity is approximately 900 meters per second. The fragments are moving far too slowly relative to each other for a standard catastrophic impact to explain their dispersal. If a body the size of Haumea had been catastrophically shattered, the pieces should be moving much faster, spread much more widely, and distributed over a much larger volume of orbital space. They are not. They are clustered tightly together, moving at speeds that suggest they were ejected gently rather than blasted apart. This velocity mismatch was the first crack in the straightforward impact model. And the deeper researchers dug, the more cracks appeared. There is also a timing problem. The Kuiper belt today is sparsely populated. The probability of two bodies the size of Haumea colliding in the current Kuiper belt over the entire age of the solar system is less than 1 in 1,000. A catastrophic collision of this magnitude should be almost impossibly rare under present conditions. The numbers simply do not favor it. But the Kuiper belt was not always as it is today. Billions of years ago, during the early history of the solar system, the region beyond Neptune was far more densely populated. The primordial Kuiper belt contained vastly more material than what remains today. Neptune's outward migration, which sculpted the Kuiper belt into its current configuration, scattered most of that material, flinging objects inward toward the giant planets or outward into the scattered disk and beyond. In the primordial, dynamically cold belt, collisions were far more frequent. A large impact could have occurred during that earlier, denser era with reasonable probability. But this introduces its own complication. If the collision happened in the primordial belt, before Neptune's migration disrupted the region, the resulting family should have been scattered and stirred by Neptune's subsequent gravitational influence. The tight orbital clustering that defines the family should have been erased. The fact that the family members still cluster together today suggests either that the collision happened after Neptune's migration was largely complete, when the belt was already sparse and collisions were improbable, or that some mechanism preserved the family's coherence through the migration. This contradiction, a collision that needs to happen early enough to be probable, but late enough for the family to survive, drove researchers toward alternative models. In 2009, Hilke Schlichting and Riem Sari proposed a scenario that resolved part of the problem. In their model, the giant impact did not directly eject the family members from Haumea's surface. Instead, the impact created a single large moon, which then tidally evolved outward from Haumea over time. As this original moon migrated to larger orbital distances, it became more vulnerable to secondary collisions with passing Kuiper belt objects. Eventually, a subsequent impact destroyed this original moon, and its fragments became the family members we observe today. Because the fragments were ejected from a moon in orbit around Haumea, rather than from Haumea's surface, their velocities relative to each other were naturally lower than the escape velocity from Haumea itself. The velocity dispersion problem was solved. This model had the additional advantage of decoupling the timing of the original giant impact from the timing of the family's creation. The giant impact could have occurred early in the primordial belt when collisions were frequent. The original moon could then have survived for a long time, tidally evolving outward, until a second smaller impact destroyed it and created the family much later. This later creation could have occurred after Neptune's migration, preserving the family's orbital coherence. But even this model left questions unanswered. How likely was it that the original moon would be destroyed by a secondary impact? What were the properties of that original moon? How did the current moons, Hi'iaka and Namaka, form in this scenario? Were they fragments of the destroyed original moon, or were they produced by a separate process? The most comprehensive answer came in 2022, when Benjamin Proudfoot and Darren Regozin published a study in Nature Communications that proposed a fundamentally different formation scenario. Their model began not with a simple impact, but with a binary system. two large icy bodies orbiting each other in the early Kuiper belt. Binary systems are common among Kuiper belt objects. Observations suggest that a significant fraction of large trans-Neptunian objects exist in binary or multiple configurations. Two bodies of comparable size orbiting a shared center of mass. These binaries are thought to have formed during the early stages of the solar system, possibly through gravitational collapse within the protoplanetary disk or through gentle capture mechanisms in the dense primordial environment. In Proudfoot and Ragozin's model, the proto-Haumea began as one such binary. Two large icy bodies orbited each other. Then, through a process that could have been triggered by gravitational perturbations from Neptune's migration or by the natural tidal evolution of the binary orbit, the two bodies collided at a grazing angle. The collision was not catastrophic. It was what planetary scientists call a graze and merge event. The two bodies struck each other at a shallow angle, partially disrupting their outer layers while merging their dense, rocky cores into a single, rapidly spinning body. The angular momentum of the original binary orbit was converted into the spin angular momentum of the merged body, explaining Haumea's extreme rotation rate. The icy material stripped from the outer layers during the merger was ejected at low velocity, forming a disk of debris around the newly merged body. Some of that debris coalesced into the moons. Some of it was scattered into independent orbits, becoming the collisional family. This model solves problems that earlier scenarios could not. The graze and merge collision naturally produces a rapidly spinning body. It naturally strips icy material from the surface while preserving the denser rocky interior, explaining why Haumea has a differentiated structure with a rocky core and an icy mantle, and why the family members are composed of nearly pure water ice rather than a mixture of rock and ice. The ejection velocities of the debris are naturally low because the collision is grazing rather than head-on, solving the velocity dispersion problem without invoking a secondary event. The timing problem is also addressed. In the Proudfoot and Ragozin model, the binary merger occurs near the end of Neptune's orbital migration. The merger event itself produces a unique orbital signature, a clustering in orbital element space that would be recognizable if preserved. But the final stages of Neptune's migration effectively erase this signature, scattering the family members just enough to destroy the telltale orbital pattern of a binary merger, while preserving the broader family clustering. The result is a family that looks dynamically coherent, but whose specific formation mechanism has been disguised by Neptune's gravitational influence. This is the current leading model for the formation of the Haumea system, though it remains a hypothesis, not a confirmed fact. The evidence supports it. The physics allows it. The orbital dynamics are consistent, but direct proof, the kind of definitive confirmation that would close the debate, has not yet been achieved. The formation of the Haumea family remains, in the formal scientific sense, an open question. What is not open is that something happened. The family exists. The moons exist. The ring exists. The spin exists. The shape exists. The surface composition exists. All of these must be explained by the same event or sequence of events, and every viable explanation involves violence on a scale that transforms the body entirely. Now, step back and look at what the collision left behind. The merged body settled into a differentiated state, its rocky core sinking to the center, its icy mantle wrapping the exterior. Its rotation, imparted by the angular momentum of the binary orbit, stabilized at approximately 3.9 hours per revolution. The outward centrifugal effect of that spin stretched the body along one equatorial axis, pulling it into the triaxial, Jacobi-like shape we observe today. The surface, freshly exposed ice from the disrupted outer layers, remained bright and crystalline, lacking the dark, irradiated coating that accumulates on undisturbed Kuiper Belt surfaces over billions of years. The debris disk that formed in the equatorial plane partially coalesced into two moons, Hika and Namaka, both icy, both orbiting in the equatorial plane, both carrying the compositional signature of the material that was stripped from the parent bodies during the collision. Remaining debris settled into a narrow ring at the 3-to-1 resonance with the spin, a stable orbital niche carved out by the gravitational harmonics of the elongated central body. And the fragments that escaped Haumea's gravity entirely drifted outward into the Kuiper Belt, following similar orbits, carrying the same icy composition, gradually spreading apart over billions of years, but never fully losing their family resemblance. Every piece of this system carries a record of that event. The shape records the angular momentum. The surface records the disruption. The moons record the debris disk. The ring records the resonant structure of the gravitational field. The family members record the ejected material. None of these features exist in isolation. They are chapters of the same story, written in different physical media but telling the same narrative of a world that was violently remade and has carried the evidence ever since. There is a comparison that may help bring this into focus, not as an analogy but as a parallel event in a different part of the solar system. Roughly 4.5 billion years ago, a body approximately the size of Mars, called Theia, struck the young Earth at a grazing angle. The collision partially merged the two bodies, blasting enormous quantities of material into orbit around the newly combined Earth. That orbiting debris coalesced into the Moon. The impact delivered angular momentum that set the Earth-Moon system spinning. The event shaped the Earth's internal structure, influenced the formation of its core, and left behind a moon whose composition is closely related to Earth's mantle. 4.5 billion years later, the evidence is still visible. The moon is still there. The Earth is still spinning. The angular momentum is still conserved. Haumea's story is the same kind of story, told in a different place, under different conditions, with a different outcome. A large collision in the outer solar system merged two bodies or catastrophically disrupted one. The angular momentum of the event set the resulting body spinning faster than anything else of its size in the solar system. The stripped material formed moons, a ring, and a scattered family. The surface was refreshed. The interior was differentiated. And 4.5 billion years later, the evidence is still there, encoded in the shape of a body that gravity has never managed to round. What Haumea tells us, beyond the specific physics of its own formation, is something broader and more important about the Kuiper Belt and the outer solar system. For most of the history of planetary science, the Kuiper Belt was treated as a frozen archive, a collection of inert, ancient, undifferentiated icy bodies sitting in the dark, unchanged since the formation of the solar system. The assumption was that nothing interesting happened out there after the initial period of planet formation ended. The real action was in the inner solar system. The giant impacts, the volcanic resurfacing, the tectonic activity, the atmospheric evolution, All of that belonged to the planets and their large moons. The Kuiper Belt was the attic, dusty, cold, forgotten. Haumea shatters that assumption. Here is a world that experienced a collision violent enough to completely restructure its body, reshape its surface, spin it to the edge of rotational stability, and scatter fragments across millions of kilometers of the outer solar system. Here is a world that carries not one, but multiple independent records of that event. In its shape, its spin, its moons, its ring, and its collisional family. Here is a world whose internal structure, a differentiated rocky core beneath an icy mantle, demonstrates that the physical processes of heating, melting, and separation that operate inside the terrestrial planets also operated in the frozen outer reaches of the solar system, even on bodies far smaller and far colder than Earth or Mars. And Haumea is not likely to be unique. It is simply the most dramatic example. The Kuiper Belt contains thousands of objects that have never been studied in detail. Some of them may carry their own records of ancient collisions, encoded in their shapes, their compositions, their rotation rates, their satellite systems. Haumea is the one we found first because its signatures are so extreme that they announce themselves through even the crude measurements available from billions of kilometers away. A light curve that swings by a third every few hours. A surface that is too bright and too icy. A rotation rate that is too fast. These anomalies drew attention. They demanded explanation. And the explanation revealed a history as violent and complex as anything in the inner solar system. The Kuiper Belt is not an attic. It is a crime scene. And Haumea is the evidence that has been sitting in plain sight, spinning in the dark, waiting for someone to read it. There's one more dimension to this story that deserves attention, because it reaches beyond the physics and into the question of what we expect when we look at the outer solar system. When the International Astronomical Union defined the dwarf planet category in 2006, the implicit assumption was that these bodies would be roughly round, spherical, settled. Gravity would have done its work. They would be smaller and less massive than the 8 major planets, but they would share the same basic geometric outcome. A shape dictated by the equilibrium between gravity and internal pressure, modified only slightly by rotation. Haumea forces us to reconsider that expectation. It qualifies as a dwarf planet. It is massive enough for gravity to have shaped it. It has, by every physical criterion, reached hydrostatic equilibrium. But the equilibrium it reached is not a sphere. It is not even close to a sphere. It is a distorted triaxial body whose shape reflects not just the inward pull of gravity, but the outward push of a rotation so extreme that it has permanently deformed the body away from the form that gravity alone would impose. This means that a dwarf planet is not necessarily a small round world. It can be a fast, stretched, flattened, elongated object that carries the shape of its history in its very geometry. The word planet, in any form, carries an intuitive expectation of roundness. Haumea breaks that expectation while still satisfying the formal definition. It is round in the technical sense that gravity has dominated its shape. But it is not round in any sense that a human eye would recognize. And the reason it is not round is not because gravity failed. It is because something else intervened. Something violent enough to overpower gravity's preference for spheres and impose a different equilibrium entirely. That intervention, the collision or merger event that set Haumea spinning, is not an exotic or implausible mechanism. Collisions are a fundamental process in planetary science. The moon formed through one. The Martian dichotomy, the dramatic difference between Mars's northern and southern hemispheres, may have been shaped by one. Mercury's anomalously large iron core may reflect one. Uranus's extreme axial tilt, lying nearly on its side as it orbits the Sun, is best explained by one. Collisions are how the solar system was built. They are how planets were assembled from smaller bodies, how moons were created, how surfaces were resurfaced, and how angular momentum was distributed among the surviving bodies. Haumea simply demonstrates that this process operated in the outer solar system as well, and that its consequences are preserved with extraordinary fidelity at the frozen temperatures and low collision rates of the Kuiper belt. In the inner solar system, the evidence of ancient impacts is gradually erased by geological activity, atmospheric weathering, and tectonic resurfacing. On Earth, the Theia impact left behind the moon, but no visible scar on Earth's surface. Plate tectonics, erosion, and volcanic activity have long since overwritten the geological record of that event. In the Kuiper belt, there is no such erasure. The temperatures are too low for geological activity. The surfaces are too stable for significant weathering. The collision rates are too low for subsequent impacts to overwrite the original signatures. What happened stays. The evidence persists. The rotation rate does not change. The shape does not relax. The surface composition does not get buried. The moons do not drift away. The family members do not disperse beyond recognition. The record is frozen, preserved in the same cold vacuum that preserved the icy material of the Kuiper belt itself. Since the formation of the solar system, Haumea is, in this sense, a fossil. Not a fossil in the biological sense, but a physical fossil. A body whose current form preserves the shape of forces that acted on it billions of years ago with a fidelity that would be impossible anywhere in the warmer, more dynamic inner solar system. Its elongated body is a cast of the angular momentum imparted by the collision. Its icy surface is the exposed interior of a differentiated world whose outer layers were partially stripped away. Its moons are the coalesced remnants of the debris disk that formed in the equatorial plane. Its ring is the surviving trace of material trapped at a gravitational resonance carved by the rotating elongated body. Its collisional family is the population of fragments that escape the system entirely, but could not escape the orbital fingerprint of their origin. Everything about Haumea is evidence. Everything is a record. Everything points backward in time to an event that we did not witness, but whose consequences we can read as clearly as a scar on skin. And the most unsettling part of this story is not the violence itself. It is that the violence was ordinary. Collisions of this magnitude were common in the early solar system. They built the planets. They shaped the moons. They distributed the angular momentum that determines how every body in the solar system spins and orbits today. What makes Haumea unusual is not that it was struck, it is that the evidence survived. In the frozen outer solar system, at minus 241 degrees Celsius, more than 40 astronomical units from the Sun, there is nowhere for the evidence to go. It simply endures. 4.5 billion years after whatever event created it, Haumea continues to spin. Once every 3.9 hours, its elongated body turns in the dark, presenting its long axis, and then its short axis, and then its long axis again, over and over, an endless rotation that carries the angular momentum of a collision that predates every living thing, every civilization, every species that has ever existed on Earth. Its moons orbit in the equatorial plane, held by the same gravity that fights the spin. Its ring circles at the 3-to-1 resonance, a delicate band of particles maintained by the interaction between the ring's orbital motion and the gravitational harmonics of the body it encircles. And scattered across the Kuiper belt, a family of icy fragments follows similar orbits, carrying the same spectral fingerprint, moving at velocities that record the gentleness of their ejection from a system that was being torn and remade by forces that only last for moments, but whose consequences persist for the age of the solar system. This is what Haumea is. Not an oddity. Not a curiosity filed away under unusual shapes. It is a damaged world. A surviving remnant of the outer solar system's violent formative period. A body whose present appearance, down to the exact ratio of its 3 unequal axes, is the frozen aftermath of an ancient catastrophe. The spin is the memory of the impact. The shape is the consequence of the spin. The moons are the children of the debris. The ring is the echo of the resonance. The family is the scattered evidence. And if you could somehow stand at the edge of Haumea's icy surface, balanced against the weak gravity and the centrifugal push of its rapid rotation, and you looked out across the dark expanse of the Kuiper belt, you would see nothing. No other world visible to the naked eye. No sunlight strong enough to warm your face. Just darkness in every direction, punctuated only by the faint, steady glow of stars so distant they barely flicker. But the body beneath your feet would be telling a story, not in words, not in symbols, in shape, in spin, in the crystalline structure of the ice beneath you, and the ring of particles circling overhead, and the 2 small moons tracing their patient orbits through the dark. Every feature a sentence, every measurement a paragraph, every orbit a chapter in the history of a world that was broken and remade and has been carrying the shape of that violence, turning once every 3.9 hours in the frozen silence, for longer than life has existed on Earth. The Kuiper belt is not empty. It is not quiet. It is not a graveyard of frozen leftovers with nothing left to say. It is a library written in ice and rock and angular momentum, and Haumea is its most dramatic volume, sitting on the shelf, spine cracked, pages open, waiting to be read. We are only beginning to turn the pages,